Hello students, today we are going to discuss moving charges and magnetism, NCERT section 4.5 to 4.6 and examples 4.5 and 4.6. This is disclaimer. So what are the learning objectives from our today's topic? After studying this chapter, students will be able to derive and apply the formula for magnetic field at any point on the axis of a circular current loop, understand how magnetic field varies with distance along the axis of current loop, state and explain Ampere's Circuital law. So here is the index, the topics that we are going to discuss today. So NCERT section 4.5, magnetic field and axis of circular current loop. Then example 4.5, then example 4.6, and then NCERT section 4.6, Ampere Circuital law. So the first topic that we are going to discuss is NCERT section 4.5, magnetic field of axis on the axis of circular current loop, and it is also application of Biot-Savart's law. So you can see a figure 4.9 representing a circular loop. Okay, so we have to find the magnetic field. We have to derive the expression to find the magnetic field at point P on the axis of this circular loop. Okay, so magnetic figure 4.9, magnetic field on the axis of current carrying circular loop of radius R. So radius of this circular loop is capital R. Shown are the magnetic field dB. What is dB? Is the magnetic field due to small line element dl and its components along the perpendicular to the axis. Okay, so dB is being shown at point P on the axis of circular loop and its components along the axis and perpendicular to the axis is shown. So magnetic field due to circular coil along its axis is determined by the summing up the effect of very small current elements ideal. Okay, so there are very small, we are going to consider, like we have done in the previous lecture, that we are going to consider very small current element dl on this current loop, and we are going to find the magnetic field due to this small current element dl at point P, which will be dB. Okay, then we will sum up the magnetic fields due to all the small elements on this circular loop and find the net magnetic field at point P. Okay, so according to Biot-Savart law, what we are going to do? We are going to determine the small magnetic field due to small element dl first. So we assume that current I is steady and circular loop is placed in free space. Okay, so current I is not varying. It is constant over time. That means steady current. Okay, and circular loop is placed in vacuum. So figure 4.9 is showing a circular loop carrying steady current I. Okay, you can see it is placed in YZ plane. This diagram is 2D, but you have to imagine this diagram in 3D. Okay, so we are considering all the three axes X, Y, and Z. This loop, circular loop, is placed in YZ plane. Okay, so which is YZ plane? Perpendicular to the plane of paper. You are seeing the screen. So this YZ plane is perpendicular to your screen. Okay, so this loop is placed like this, perpendicular to your screen. So it is placed in YZ plane. You can see in the diagram also, with its center at origin. Okay, we are going to use Cartesian coordinate system X, Y, Z. So coil is placed in YZ plane and its center is at origin O. Okay, and its radius is capital R. Now, what is x-axis representing here? Axis of loop, because center of loop is at origin. Center of the circular loop is at origin. So what its axis is lying on x-axis. Okay, so x-axis is passing through origin. So the axis of the loop is along the x-axis. Okay. So what we are going to calculate magnetic field at point P on the axis of loop. Okay, so P is some point at the axis of loop at some distance x from the center of the loop. So let x be the distance of point P from the center of the loop. Got it? Now you can visualize this diagram. Loop is placed in YZ plane and its axis is along x axis. Okay, and P is the point at a distance x from the center O. And what is R? R here is distance of P point from the current element DL. That current element we are going to consider small current element on this loop. The R distance is the distance between point P and this DL current element. Okay. Now consider a conducting element or current element DL of the loop. The magnitude dB of the magnetic field due to DL is given by Biot-Savart's law. Okay, now we know that due to a small current element, as we have done in the previous lectures, due to small current element, the magnetic field at a point in the space is given by the Biot-Savart's law. Okay, so magnitude of dB of magnetic field due to this small current element DL is given by the Biot-Savart's law. So what is Biot-Savart law? dB is equal to, that dB is magnitude only. Okay, and direction is can be found using right hand rule. Okay, so we are dealing with magnitude as of now. We will discuss about direction also. Okay, so dB, magnitude of this small magnetic field produced by small element DL is mu naught upon 4 pi I, and DL cross R, the magnitude mod around DL cross R represents the magnitude of this cross product. Okay, upon R cube. Mark it as 4.8 equation. Now here from the figure 4.9 you can see what is this Pythagoras theorem. Apply the Pythagoras theorem between in this triangle OP and this DL current element. So you will get small r square, which is hypotenuse, is equal to base square plus perpendicular square. So r square is equal to x square plus r square. Okay, by applying Pythagoras theorem. So from figure 4.9. So you have to put this r square in 4.8 in the further steps. So now you can see loop is in YZ plane. Okay, and this r, this displacement vector, is in XY plane. From the figure you can see we have mentioned earlier that loop is in YZ plane, and this r vector you can see is in XY plane. So this DL vector, because DL vector is on loop na. Okay, so this DL vector is in YZ plane and this r vector is in XY plane. So both DL and r vector are perpendicular. So angle between DL vector and r vector, that is displacement vector, is 90 degree. Okay, so any loop element will be perpendicular. If we take any element on the loop, any small element on the loop, it will be perpendicular to the displacement vector, because in each case displacement vector will be in XY plane and in each case DL vector will be in YZ plane, because loop lies in YZ plane. So any loop element will be perpendicular to the displacement vector from the element to the point P. Got it? So angle between DL and R is 90 degree. So for example, figure 4.9, element DL is in YZ plane, whereas the displacement vector R from DL to the actual point P is in XY plane. Okay, R is in XY plane, DL is in YZ plane. Hence, DL cross R, the magnitude of this DL cross R will be R DL sin theta. Magnitude of this DL cross R will be R DL sin theta, and because theta here is 90 degree, so sin 90 degree is 1. So it will remain RDL. We will get RDL. Does. Now putting the value of DL cross R and R square equal to X square plus capital R square, we will get this. So dB equal to mu naught upon 4 pi IDL upon X square plus R square. Mark it as 4.9 equation. In 4.8 equation, what was given? dB is equal to mu naught by 4 pi I dl cross R upon R cube. dl cross R will become RDL, and 1 R will in numerator will get cancel with the R cube, then R square will remain in the denominator. Okay, so it will become mu naught by 4 pi I dl upon small r square. So small r square is x square plus capital R square. So we will get the equation 4.9. Now, the direction of dB. Now you can see in this diagram, direction of dB is perpendicular to the plane formed by dl and r. Okay, so plane formed by dl and r. dl is in outward direction. If we consider the dl at the top of the loop, it is in outward direction. It is in along z direction. So it is along outward direction. And r is along in xy plane from dl to r. So the plane formed by these two vectors will be, okay, assume, visualize the plane formed by both these. So it is outwards and it is inclined to x-axis. dl is outwards along z-axis and r is inclined to x-axis. So the plane formed by this will be inclined to xz plane. The plane formed by dl and r will be a plane that is inclined to xz plane. Okay, so this xz plane that is inclined to xz plane, the dB will be perpendicular to that plane. Okay, so this line representing the direction of dV is perpendicular to the plane formed by dl and r. Okay, and the plane formed by dl and r is the plane that is inclined to the xz plane. Okay, you can visualize. So dB is perpendicular to that. Okay, or we can say dB is perpendicular to the displacement vector r. It is also represented in the diagram. dB is perpendicular to the displacement vector. Okay, and it is also perpendicular to dl. You can assume that also. Okay, if you are not understanding this plane term, that dB is perpendicular to the plane formed by dl cross r and dl and r, you can also interpret in this thing with other words, that dB is perpendicular to both dl and r. Okay, it is perpendicular to r. It is represented in the diagram. How it is perpendicular to dl? Because dl lies in the other plane. dB is perpendicular to that plane. So dB is perpendicular to dl also. Got it? So magnetic field dB has an x component. Now we will resolve this dB into two components. First, a x component. This dB has an x component, dBx, which is along the axis of loop and away from the center. You can see in the diagram, it is in the positive x direction. Okay, so x component is represented by dBx, which is along the axis of loop and away from the center. And second component is perpendicular to x-axis, that is dB perpendicular. That is perpendicular component of dB. Now, perpendicular components cancel out when summed up over the loop, giving the null result, leaving only the x component. Now you can see, if we consider the dl vector which is shown in the diagram at the lowest point of the loop, which is diametrically opposite point. Okay, two dl are shown in the diagram. first is at the top of loop, but second is at the lowest point of the loop. Okay, we are considering or we are deriving the expression for topmost element. Now if we consider the element at the lowest point of the loop dl, which is exactly diametrically opposite to the above dl element, so due to this lowermost dl point, dl element, the magnetic field will be in the direction, it will be shown as this. If this dB is shown in this direction, then due to this dl, the magnetic field will be shown as at this point, as this, like this. Okay, so this dB will also get resolved. One component will be along dbx due to this lowermost dl. Due to this lowermost dl element, their dB is in this direction, in the downward direction. It will get resolved into two components. One is along x axis and second is perpendicular to x axis but in the downward direction due to this lowermost dl. Okay, so this lowermost dl is exactly opposite to the uppermost dl. Okay, so if we take any element dl on the loop, there is exactly opposite dl exists. If I consider the dl element here, then at exactly opposite point there is dl also. Okay, so the perpendicular components cancel out. Okay, when summed up over a loop, when we take all the elements on the loop, there are equal and opposite components existing. Okay, so the magnetic field component, perpendicular component of magnetic field will be cancelled out by the other opposite dl over the whole loop. So the perpendicular components cancel out when summed over the loop, giving a null result, while leaving only the x components. Only components that are along x axis remain with us. Okay, the perpendicular magnetic field component dB perpendicular from opposite current dl elements cancel each other out as shown in the figure 4.9. Okay, so all the perpendicular components will be cancelled out, like it is written. The perpendicular magnetic field component dB perpendicular from opposite current element that is existing exactly opposite to that element due to the symmetry of coil, due to the symmetry of loop, from the opposite current dl elements cancel each other out as shown in the figure 4.9. The net contribution is along x direction comes from integrating dbx. Okay, equal, what is dbx? If the angle between db and x axis is theta. Okay, so what is dbx? db cos theta. Okay, so we have to integrate dbx over the whole loop. Okay, this dbx is due to very small element on the loop. Due to all the elements on the loop over the whole loop, over the entire loop, we have to integrate the dbx, which is equal to db cos theta over the loop. So from figure 4.9, cos theta. Okay, so what is cos theta? So angle between dB and x is theta. Okay, also angle between, by using geometry, you can find that angle between dB perpendicular, this dB perpendicular and this r, this angle between these two, this r and this dB angle is also theta. You can find it by geometry. So this theta is representing, so we have to find the cos theta for this theta. So cos theta is base upon hypotenuse. So what is the base for this theta? This thing. this thing. Okay, and what is the hypotenuse? R. Okay, base is this R, capital R, and hypotenuse is this small r. Got it? Now cos theta will be capital R upon small r, and we know that small r square is equal to x square plus capital R square. So r will be x square plus capital R square under root. So x square plus capital R square 1 by 2 raised to power 1 by 2, that is under root in square root. And this is the cos theta value 4.10. So you have to put the value of dB that we have found in equation 4.9 and cos theta that we have recently found. You have to put these two values in this dB cos theta and find the dBx. So from equation 4.9 and 4.10, we can say dBx is equal to, put the value of dB. What was dB? Mu naught I dl upon 4 pi. Okay, so what is cos theta here? This is the value of dB. Also x square plus r square was there. What was dB? Mu naught I dl upon 4 pi x square plus r square. And what was cos theta? R upon x square plus r square raised to power 1 by 2. Now x square plus r square raised to power 1 into x square plus r square raised to power 1 by 2. So their powers will get added and result in 3 by 2. So dBx is equal to mu naught I dl upon 4 pi into r upon x square plus r square raised to power 3 by 2. So this is dBx. Now this is due to the small elements. Now we have to integrate it. So summing dl elements over the loop gives. So you have divided the loop into very small elements. Now you are going to sum up. So it will result in the perimeter of loop. So what is the perimeter of loop? 2 pi r. It is in the circular form. So perimeter of the loop is, so if we are summing it, integrating it or summing it. So this mu naught is constant, 4 pi is constant, current is steady throughout the coil. R is constant. We have to find the, we have fixed the x where we want to find the magnetic field, and R is also fixed. So what is not, what is going to summed up? This dl. So this dl will be summed up over a whole loop. So the perimeter of loop will be 2 pi r. So replace dl with 2 pi r and this dBx with B. So does the magnetic field at point P due to entire circular loop is given by B, which is equal to, the magnetic field direction is in, because perpendicular components are cancelling out. Only components along the x axis remain with us. So the direction of net magnetic field will be in the direction of positive x direction. So net magnetic field is equal to Bx I cap. Bx is the magnitude and I cap is the direction. What is I cap? Unit vector of x-axis. So its direction, net magnetic field has direction along the x-axis due to this current loop. So B equal to Bx I cap equal to mu naught I r square. Okay, so 2 pi r, after putting 2 pi r. So pi and pi will get cancel out and this 2 and 4 will also get cancel out. So it will become mu naught I r square upon 2 x square plus r square raised to power 3 by 2 I cap. So it is in vector form. Direction is also mentioned. And mark it as equation 4.11. Now this is figure 4.10 and the magnetic field lines of a current loop, the direction of the field is given by right hand thumb rule. We can find the direction of magnetic field at the center of the loop or anywhere by using right hand thumb rules described in the text. The upper side of the loop may be thought as the north pole and the lower side of the loop can be considered as south pole of the magnet. Okay, now there is a trick. If the current is, you are facing you are facing some end of the loop. Okay, if the current on the phase of loop which you are facing, which you are seeing, if the direction of current is anti-clockwise, then this phase of the loop, that end of the loop is north pole. If direction of current is clockwise, then end of the loop is south pole. Okay, if you are viewing the loop from any end and the direction of the current at that end is anti-clockwise, then pole is north pole. If the direction of current is clockwise, then the pole is south pole. Got it? So it is a special case. So at loop center where x is equal to 0, x is the distance from center to point P. If we are want to find the magnetic field at center, then x will be 0. So magnetic field at center of the loop is given by putting x equal to 0 in the equation 4.11. So we will get B naught, which is magnetic field at center, equal to mu naught I upon 2r I cap. Got it? Mark it as 4.12 equation. The magnetic field lines due to a circular wire form closed loops. Okay, due to this circular loop, magnetic field lines are in the form of closed loop. You can see in the diagram, blue lines. Direction of magnetic field is given by right hand thumb rule. So what is right hand thumb rule? You have to curl your right palm of your right hand. You have to curl your right palm around the circular wire. Okay, with fingers pointing in the direction of current. You have to curl your palm and such that fingers are pointing in the direction of current. Okay, and then thumbs give the direction of magnetic field. In this diagram, if you are curling your fingers in the direction of current, that is anti-clockwise. Okay, so direction of current will be in upward direction. Your thumb will point in the upward direction. Okay, so you can find the direction of magnetic field for a current carrying loop. Got it? Now example 4.5. A straight wire carrying current of 12 ampere is bent into semicircular arc of radius 20 centimeter, 2 centimeter, as shown in the figure 4.11a. Consider the magnetic field B at center of the arc. What is the magnetic field due to straight segments? So this is the figure 4.11. We have to find the magnetic field due to the straight segments in the A diagram. Figure 4.11a part. We have to find the magnetic field due to straight segments. So A part, dl and r for each element of the straight segments are parallel. Okay, so if we are considering some dl element on the straight segments, these straight at the ends of this loop, so we are considering dl element, small dl element on the straight segments. So from the center, if we are drawing a displacement vector from center to this dl, so the direction of dl and direction of this position vector or displacement vector will be parallel or anti-parallel. Okay, so for this parallel, for this segment anti-parallel. So dl and r for each element on the straight segments are parallel or anti-parallel. That is, theta will be 0 or 180 degree. Therefore, dl cross r, magnitude of dl cross r will be r dl sin theta, and if theta is 0 degree or 180 degree, then this term will become 0, because sin 0 and sin 180 is 0. So straight segment do not contribute to B. So in this diagram, only this arc, semicircular loop, will contribute to the magnetic field. These straight conductors are not contributing to magnetic field. Okay, so this is now B part and C part. So of the same question, B part, in what way the contribution of to B from the semicircle differs from that of circular loop, and in what ways it resembles? We have taken the semicircular loop, and in what way the result for the semicircular contribution due to the semicircular loop differs from the complete circular loop, and what way does it resemble? And C part is, would your answer be different if the wire were bent into a semicircular arc of the same radius but in the opposite way as shown in figure 4.11b? Okay, so if we bend the loop and of say semicircular arc of same radius as in figure 4.11a, but in the opposite direction as shown in the figure 4.11b, so what would the answer be different? So let's do it. So for all segment of semicircular arc, dl cross r are parallel, all parallel to each other into the plane of paper. Okay, you can see the magnetic field direction due to this circular loop by using right hand thumb rule, or you can say due to all segment, if you are considering small segment on this semicircular loop dl, then dl cross r will be parallel to each other due to all elements, or you can find the direction by right hand thumb rule. So at the center of this semicircular loop, the direction of magnetic field will be into the plane of paper. All such contribution add up in magnitude. Due to small elements you are considering on this semicircular loop, all such contributions add up in magnitude. So hence direction of B for a semicircular arc is given by right hand thumb rule. Okay, as I've already mentioned that you can find the direction by using right hand thumb rule also. So what is the direction? Into the plane of paper. Okay, so magnitude is half as compared to the circular loop. Due to complete circular loop, magnetic field will be some, you can say B. Okay, so due to this semicircular, because loop is becoming half, it is semicircular loop, so magnetic field will always also become half. So magnitude of magnetic field is half of the as compared to circular loop. So B is 1.9 into 10 to the power minus 4 Tesla, normal to the plane of paper going into it. Okay, so we have found the magnetic field by using the formula mu naught I upon 2r, that is for circular loop. Okay, and current is given, radius is given, and you can find by using mu naught I upon 2r. By putting the values, you can find the magnetic field due to circular loop at the center of circular loop, and due to this semicircular loop, magnitude will be half of that found value. Okay, so B is 1.9 into 10 to the power minus 4 Tesla. For complete circular loop, it will be 3.8 into 10 to the power minus 4 Tesla. Okay, and direction is normal to the plane of the paper going into it. And C part, if we are placing this semicircular loop in the opposite way, so the magnitude of magnetic field will remain same, but direction will change. You can apply the right hand thumb rule and you can see that thumb is pointing towards you. So now direction is normal to the plane of paper and coming out of it, but magnitude remains same as B. Okay, example 4.6. Consider a tightly wound 100 turn coil of radius 10 cm carrying a current of 1 ampere. What is the magnitude of magnetic field at the center of the coil? Since the coil is tightly wound, we may take each circular element to have the same radius. Okay, it is tightly wound, so radius of each circular segment is same, which is capital R, equal to 10 cm, and in SI unit it is 0.1 meter. The number of turns N equal to 100 and current is given 1 ampere. So the magnitude of magnetic field is mu naught I upon 2r. Due to one circular loop, magnitude of magnetic field at the center is mu naught I upon 2r. Due to a coil that is having n number of turns, so you have to multiply it with number of turns also. Mu naught I upon 2r is magnetic field due to one circular segment, and due to n number of turns, you have to multiply it with n. So due to n number of turns, magnetic field will be mu naught n upon I upon 2r. So after putting the values, b equal to 4 pi into 10 to the power minus 7, value of mu naught by 4 pi is 10 to the power minus 7, and value of mu naught will be 4 pi into 10 to the power minus 7 into 10 to the power 2, which is number of turns, into 1, which is current, upon 2 into 10 to the power minus 1. So it will result in 2 pi into 10 to the power minus 4. So magnetic field will be 6.28 into 10 to the power minus 4 Tesla. So now the next topic, NCERT section 4.6, Ampere's Circuital law. And it is used to find the magnetic field around a current carrying conductor. So this is the figure 4.12. You can see. Okay. Ampere's circuital law considers an open surface with a boundary where current passes through it. Okay. So there is a surface, open surface, you can see in the diagram, and you can consider it as like there is a lemon. You have cut it, but not from the halfway. You have cut it from some end. Okay. So one end is open now. Okay. So you can consider this surface as that thing. You have cut the lemon from an end, not from center, not from exactly center, but from towards center. Okay, the cut part, the part which is being cut is small than the actual part remaining. So this is the surface like that. So Ampere's circuital law considers an open surface with a boundary where current passes through it. So this is a boundary represented in the diagram also. Okay, so this is the surface which is shaded part, and this is boundary from which current passes. The boundary consists of small line elements. So this is the boundary, is round shaped, circular boundary. Okay, so it consists of small line elements. You can divide this boundary into small line elements, with each element of length dl having a tangential component of magnetic field bt. At each dl, very small length element dl, at each dl there is a tangential component of magnetic field bt. The product of bt and dl, this is the Ampere's circuital law. Okay, so it is having no derivation. It is law. It is given by experimental results. Okay, it has no derivation. So you have to do like that. So the product of bt and dl, that is b dot dl, for all elements are added together. Okay, so the magnetic field due to this current, flowing current, so this flowing current will produce the magnetic field. So the product of this magnetic field and this small element dl, that is b dot dl, for all the elements, small elements on this boundary, will be added together. Okay, so magnetic field bt will have tangential component along each element dl. Got it? So their b dot dl will be dot product b dl cos theta. Since tangential component of bt is along dl, so bdl cos theta will become bdl cos 0 degree, because bt is tangential to dl at every small element dl. So the angle between dl and b will be 0 degree. So we consider the limit that the lengths of the elements get smaller. Okay, we are going to integrate it. And the condition for integration is length of elements get smaller and their number gets larger. And sum then tends to integral. Okay, so if we are decreasing the length of the elements to a very small value and increasing the number of elements, then this normal sum of elements will tends to integral. So Ampere law states that the integral of b dot dl is equal to mu naught times the total current passing through the surface. Okay, now you can draw the analogous with the Gauss law. What was Gauss law? The closed integral of electric field, product of electric field and surface vector, area vector, is equal to charge enclosed upon epsilon naught. That was the Gauss law. So Ampere's law resembles somewhat the Gauss law. Okay, it is analogous to Gauss law. So Ampere's law states that this integral of B dot dl is equal to mu naught times the total current passing through the surface. And mathematically it is represented like this. This is closed integral B dot dl equal to mu naught I. And this I is enclosed current by the surface or by this boundary loop. Got it? Mark it as 4.13a, where I is the total current through the surface. Now the integral is taken over the closed loop coinciding with the boundary. So this integral, closed integral, is taken over the loop, not the surface. Okay. So this integral, you are going to consider this loop. Okay, that is coinciding with this boundary C. So this closed integral is taken over the closed loop that is coinciding with the boundary C of the surface. The right hand rule determines the sign convention. Curl the fingers along the direction in which boundary is traversed. So we are traversing, we are moving along the boundary in the anti-clockwise direction. Clockwise direction as shown in the figure. So we are traversing or moving along this boundary C in the clockwise direction. So you have to curl your fingers of your right hand in the clockwise direction. Then the thumb gives the direction of the current in which current is positive. Okay, in which current is flowing. In which direction the current is flowing. That means in which direction the current is positive. So you have to curl your finger in the direction in which boundary is traversed. Traversed means traveled. In which we are traveling along the boundary. We are traveling along the this C boundary in the clockwise direction. So curl your fingers in the clockwise direction. Then your thumb is pointing in the direction of current. You can see in this current. So your thumb gives the direction in which current is positive. Okay, in which the direction of current is aligned. Okay. A simplified version applies when the Amperian loop satisfies the condition where B is tangential to the loop and non-zero constant. Okay, so simplified version is there. That thing we have learned, that consider a surface and the boundary of the surface and that thing. This is some complex terms. You have to a simpler version is there where we can consider a loop. Simple loop without considering surface. There is a loop. That boundary, you have to consider only the loop. That is called Amperian loop. Similar to Gaussian surface. We consider a surface called Gaussian surface in the Gauss law. Now we have to consider the loop called Amperian loop. So a simplified version applies when the Amperian loop satisfies the condition where B is tangential to the loop and non-zero constant. So at each point of this loop, B is tangential to the loop at every point. Okay, and non-zero constant. Okay, so B is tangential to the loop and non-zero constant, or it can be normal to the loop or it can be zero. Got it? So the simplified version is there where Amperian loop satisfies condition where B is either tangential to loop and non-zero constant. Three conditions are there. Either B is tangential to loop and non-zero constant, or it is normal to the loop or zero. Okay. for length L where B is tangential and enclosed current IE by the loop, then the equation 4.13a part. Okay, so there is an infinite wire. So of length, there is a wire, finite wire of length L where B is tangential and enclosed current IE by the loop. Then equation 4.13a is BL equal to mu naught IE. Okay, if there is a wire carrying current IE and the length of the loop is L. Okay, we are considering some special case. If length of the loop that we are considering is L, where B is tangential to this loop at every point and the loop is enclosing a current IE. Got it? You have to consider one loop. The length of the loop is L, where B is tangential at every point of the loop and it is enclosing IE current. From equation 4.13a, you can replace dl with L because we are integrating. So B L equal to mu naught current enclosed. Okay, we are integrating B dot dl. So if we are integrating the dl over the whole loop, if the length of the loop is L, so this dl after integration will be replaced by capital L. So BL equal to mu naught IE. 4.13b. Mark it as equation 4.13b. This mu naught by 4 pi constant. This constant is appeared in Biot-Savart law. The value of mu naught upon 4 pi is equal to 10 to the power minus 7 Tesla meter per ampere. Okay. It is similar to like constant in the electrostatic epsilon naught. It is mu naught, that is permeability. And the value of mu naught upon 4 pi is 10 to the power minus 7. And value of mu naught is 4 pi into 10 to the power minus 7 Tesla meter per ampere. Got it? So this mu value will be changed if we change the medium. It is medium dependent constant. Okay. Okay, now we are considering, we have derived BL equal to mu naught IE. Okay, that length is dependent upon the type of conductor and loop taken. So for an infinite current carrying wire with cylindrical symmetry. Okay, what is cylindrical symmetry? If we are considering a wire linear, like we considered in electrostatic in Gauss law, linear charge wire, the symmetry or surface around the wire is cylindrical. The Gaussian surface around the wire was cylinder. Okay, so similarly for infinite current carrying wire with cylindrical symmetry, the wire is cylindrical. Okay, the boundary of the loop chosen is a circle. We know that for a current carrying straight wire, the magnetic field lines around the wire is in the form of concentric circles. Okay, the boundary of the loop chosen is a circle. Now we have chosen an Amperian loop also as a circle. And the magnetic field lines are also in the circular concentric circular direction. Okay, so magnetic field at this Amperian loop will be tangential. At each and every point on this loop, magnetic field will be tangential. And magnetic field is tangential to the circumference of the circle or the circumference of the loop chosen. That is called Amperian loop. Okay, we have considered a current carrying wire, infinite current carrying wire. Okay, with cylindrical symmetry. Now we have considered an Amperian loop in the form of circle, and the magnetic field is also in the form of concentric circles around this wire. So magnetic field will be tangential to this Amperian loop. Ampere's law gives for equation 4.13b. Now replace L with the length of circular path, which will be 2 pi r. Okay, r is the radius of this Amperian loop. So replace L with 2 pi r. So B into 2 pi r equal to mu naught I. I is the current enclosed by this loop. So magnetic field at a distance r outside the wire is tangential and given by B equal to mu naught I upon 2 pi r. Okay, so this is the magnetic field at a distance r outside the wire is tangential. It is tangential to Amperian loop and is given by this formula. Mark it as 4.14 equation. So key implication from the result for the infinite wire, we have derived the magnetic field for the infinite wire. So what are the key implication from the result? That magnetic field magnitude is same on the circles of radius r with wire along the axis, cylindrical symmetry. Okay, so the magnitude of the magnetic field is same on the circles of radius r with wire along the axis. If we consider a wire, the magnetic field will be in the form of concentric circles around the cylindrical wire. Magnetic field of constant magnitude form closed concentric circles unlike electrostatic field. Okay, so magnetic field will form closed concentric circles or closed concentric loops, while electrostatic field doesn't form closed loop. It starts from positive charge and ends on negative charge, but it never goes from negative to positive, means it doesn't form closed loop. But unlike electrostatic field, magnetic field form closed concentric loops. Magnetic field is finite at non-zero distance even though the wire is infinite. Even wire is infinite. We have taken the infinite wire. But magnetic field at any point at non-zero distances is finite. Magnetic field is not infinite. And right hand rule to find the direction of magnetic field due to a long wire. So we can apply the right hand rule here also. Grasp the wire, okay, in your right hand with thumb along the current direction. Fingers curl in the magnetic field direction. So this right hand thumb rule can be used in two ways. If current direction is given, you have to find the magnetic field. Then you have to curl the fingers in the direction of current, and you will get the thumb will get the direction of magnetic field. And if magnetic field is there, you have to find the direction of current. Okay, and current is there. So you have to grasp the wire and point your thumb in the direction of current, and you will find the magnetic field. Okay, you can find the magnetic field in two ways. If current is given in the form of circular loop, so you have to curl the fingers in the direction of current, and thumb will give the direction of magnetic field. In this case, you have to point your thumb in the direction of current, and the finger, your direction of curl of finger will give the direction of magnetic field. Okay, this rule can be used vice versa for current and magnetic field. So grasp wire in your right hand with thumb along the current direction. Fingers curl in the magnetic field direction. So Ampere's law relates Biot-Savart law as Gauss law relates Coulomb law. Connecting a physical quantity on the periphery or boundary to another physical quantity, namely the source in the interior. So Ampere law relates to Biot-Savart law. It is connecting a physical quantity on the periphery boundary, which is magnetic field, okay, to another physical quantity, the source, which is current. So it applies the steady current and helps calculate the magnetic fields for any loop, though not always applicable. Okay, so it helps to calculate the magnetic field around the conductors, but it is not always applicable. For example, to find the magnetic field at the center of the circular loop, we cannot find the magnetic field at the center of circular loop by using Ampere circuital law. It is only found using Biot-Savart law. So the law proves particularly useful for systems like solenoids. Okay, we are going to discuss the solenoid case in tomorrow's lecture, in the next lecture. The magnitude of magnetic field due to, so let's have a quick recap. Magnitude of the magnetic field due to circular coil of radius r carrying a current I at an actual distance x from the center is given by this formula. At the center, this reduces to B equal to mu naught I upon 2r. Ampere circuital law is given by closed integral B dot dl equal to mu naught I, where I refers to the current passing through the surface. The sign of I is determined from the right hand rule. If B is directed along the tangent to vary every point on the perimeter L of a closed curve and is constant in magnitude along perimeter, then BL equal to mu naught IE. IE is the current enclosed by the closed loop. The magnitude of the magnetic field at distance r from a long straight wire carrying current I is given by mu naught B equal to mu naught I upon 2 pi r. The field lines are concentric circles around the wire. Now some practice questions. First question, how does the magnetic field strength vary along the axis of a circular current loop as you move away from its center? Second question is, what is the relationship between the number of turns in a circular loop and magnetic field produced at its center? Third is, state Ampere's circuital law and explain. Fourth question is, how can Ampere's law be used to calculate the magnetic field around a straight current carrying conductor? Okay, so these are some practice questions you have to do yourself. And don't go anywhere, we have to do the DPP. So magnetic field at the center of a circular current loop of radius r carrying current I is given by. So I am marking the answers randomly. You can mark what is correct. So for a circular coil of radius r carrying current I, the magnetic field at a point on its axis at distance x from the center proportional to a semicircular arc of radius r carries current I. The magnetic field at its center is a tightly wound 100-turn coil of radius 10 cm and 1 ampere current. The magnetic field at its center is. So I am marking randomly. You can solve it. The direction of the magnetic field at the center of the circular current loop is determined by. So what rule is being used for the direction of magnetic field at the center of the circular current loop? Left hand thumb rule, right hand thumb rule, curling the right hand fingers in the direction with thumb indicating the field direction, or Fleming's right hand rule. So this one. A second question came out to be wrong. From the center is proportional. Okay. So it is r square upon x square plus r square raised to power 3 by 2. Okay. Because there is r square in the, according to this formula, b equal to mu naught I r square upon 2x square plus r square raised to power 3 by 2. Okay, thank you. I hope you enjoyed the session.